definite integrals. And the key will be what's called the fundamental theorem of calculus. Now it'll be in two parts, part 1 and part 2. We'll do part 1 first. And rather than give you the proof after the fact, we'll look at a development here so you'll believe that the proof is really correct and that the result makes sense. So, suppose we start on a closed interval AB as we always do. Let us suppose that we have a continuous function, f, little f, is continuous. I'll box that in. And let us suppose that we have an antiderivative of little f, big F, so that big F prime equals little f. So that is to say, f is an antiderivative. And it doesn't matter what antiderivative, as you'll see in the end. Now, let us note one other thing here, because I want to use the fact that big F is also continuous. How do I conclude that? Well, you remember we had a theorem that says big F being differentiable, as it is here, implies that big F is continuous also. And we'll use that in our argument. So the first thing we'll do is we'll start, as we often do with integrals, and talk about a partition of AB. And just to remind you of the notation, suppose we have here an interval from A to B. A might be called x sub 0, B might be called x sub n. Then we mark off an x1, an x2, and then many others. The one before B would be xn minus 1, and so on. They don't have to be the same distance apart. That's why I'm drawing them at unequal intervals. Then, if we take from in here a typical one, remember what we did. We had xk minus 1 to x sub k. The distance here was xk, the upper, minus the lower, xk minus 1, and we mark that as delta xk. Now this is all reminding you of notation we've already seen. Now, what we want to do is examine the behavior of not little f for the moment, but actually big F, which you remember now is continuous. So on each one of those intervals, those kth intervals that we looked at, on each interval, here's what we can draw. xk minus 1 here to xk. The function big F is defined there. And not only is it defined, remember, it is continuous. It is also differentiable. So let's mark that here too. So big F is continuous and differentiable over the entire interval from A to B, and certainly on each piece, like this piece. Now, if that is true, this is a continuous and differentiable function on a closed interval. That means the mean value theorem for integrals, for the mean value theorem for derivatives, that is, applies to this function. So that means somewhere in here, if we were to connect the two endpoints here of the secant, there would be some point in here, back down here on the x-axis, which we'd call xk star, where the tangent line and the secant line would be parallel. That is to say, the MVT, the mean value theorem for derivatives, applies to this function f, big F, on each interval. Since that is true, we get the relationship that says the slope of this tangent line equals the slope of this secant line, which is to say big F prime at xk star, because the slope here is the derivative at this point of this function, is equal to the slope of the secant line, which is the difference of the y values over the difference of the x values. So that's big F of xk minus big F of xk minus 1, all over xk minus 1. That's what we get from the mean value theorem. Now let's take this and continue our argument a little further. I'm going to bring the xk minus 1 up here to the left. And then I will have big F prime xk star times xk minus 1 brought up equals, and on the right-hand side we still have f of xk minus f of xk minus 1, all the time being large F. Now, a couple of notational changes. Remember that f prime, big F prime equals little f. Big F was designed to be an antiderivative of little f, so I can replace this here. I can also replace xk minus 1 because we're calling that delta xk. So that will be equal to the right-hand side here unchanged, big F of xk minus big F of xk minus 1. Now, we have one of these for each value of k. What we'll do next is we'll list them all vertically and add them up. So, we have f of x1 star delta x1 equals f of x1 minus f of a. And remember, this should be x0, but remember we took a to be equal to x0. Then the next one would be f of x2 star delta x2 equals f of x2 minus f of x1. And then you just continue this process until you get to the end. And the last one will be f of xn star times delta xn. And here we have f of b. Now that should be xn, but b was equal to xn, remember, minus the one before, which is f of xn minus 1. Now we want to add these all up. What will happen? On the left-hand side, we get the sum of the f of xk stars, they're all the same format, times delta xk, where the k goes from 1 to n. You see? 1 to n. On the right-hand side, something very nice happens. We have a collapsing sum. Notice that f of x1 and minus f of x1 add to 0. That will continue on a diagonal, f of x2 minus f of x2 and so on, all the way down to minus f of xn minus 1. That leaves us with two terms, f of b from here and minus f of a from the top step. That is very nice and very simple. Now what do we do with this? In order to get the definite integral out of this, we need to take the limit as the maximum value of the delta xk's, remember, goes to 0. That will give us the definite integral here, and we will have found that the definite integral equals the antiderivative of the integrand, little f, at b minus that at a. That is the power of the fundamental theorem of calculus part 1. So let me go ahead and write out the fundamental theorem of calculus part 1, and I will abbreviate it this way, FTC part 1. And starting out with the hypothesis we had above, if f is continuous, little f now, is continuous on AB, and big F has the property of being an antiderivative of little f, so big F prime equals little f on AB, then that limit that we said we'd take turns out to be the definite integral, of course, by definition. And that will be, well, down here it'll be f of b minus f of a, just as we discovered. But there's a middle notation here that's very helpful. It's helpful to write big F of x, so we have the function without a or b in it. And then we write a vertical bar here with a to b. And remember, we're reading a to b vertically from the bottom to the top, just as the same way we read definite integrals from the bottom to the top. And this is just a bar. This is useful notation. So you want to adapt that, and you'll see how I use it soon. And notice here, one way to remember this, which one goes first? It's upper minus lower. It's f evaluated at the upper minus f evaluated at the lower. And you see the upper and the lower here. This is it, the fundamental theorem of calculus part 1. Let me show you how this will be helpful in actually calculating definite integrals. The key, of course, is finding this, which is an indefinite integral. Here's an example. And this is what you will be doing from now on as you do definite integrals in various ways, shapes, and forms. Evaluate the definite integral from 0 to 3 of 9 minus x squared dx. Okay, how do we go about doing that using the fundamental theorem of calculus part 1? Well, if we write it down, 0 to 3, 9 minus x squared dx. This function under here is what we called in the theorem little f of x. Now what we need to do is find an antiderivative for that function. So this will be the fundamental theorem of calculus part 1 that allows us this equals. What goes in here is the antiderivative. So we have to anti-differentiate to get up to here. Well, we know how to do that. We know what functions will lead to 9 minus x squared from our experience. We know that 9x will have a derivative equal to 9, minus, and then we know that x cubed over 3 will have a derivative equal to x squared. So your knowledge of antiderivatives here will be crucial to doing definite integrals. And then what we do is we vertically put 0 and 3 because this was a and this was b in the theorem. And you notice I'm not putting an extra vertical bar here. That's another convention. If the function is itself encased in brackets, you can skip the vertical bar and just use the right bracket with the 0 and the 3. Just a convenience. What is this in here? This is any antiderivative, big F of x, of little f of x. All right, let's continue this. What we're supposed to do is evaluate this function, which is f of x, at the upper minus the lower. So that will be, first we'll have to do f of b, and then we'll have to do f of a to follow the fundamental theorem of calculus. F of b means you put b in here. So if we put 3 in here, we get 9 times 3 minus 3 cubed over 3. And here, if we put 0 in, we get 0 minus 0. That's nice. So this part here becomes 27 minus 9, and this is, of course, 0, so this becomes 18. Once again, a definite integral has turned out to be a number, of course, and we use the fundamental theorem of calculus here to compute it. The key and hardest part of this is finding an antiderivative of the function under here, and that's what you'll spend all of your time learning how to do as you learn how to do more complicated integrals. Now, before we leave the fundamental theorem of calculus part 1, let me give you a warning. It's very easy at this stage of the game to ignore the hypotheses of theorems and just start calculating away. Here you can cause yourself great difficulties if you do that. Don't ignore the fundamental theorem of calculus part 1 hypotheses. And just to make sure you understand that, let me give you an example of where things could go wrong. And this could easily trip you up. Suppose we have a function like 1 over x squared. Perfectly nice function. And let us go ahead and examine it on minus 1 to 1. Now, observe the following. First of all, f is not defined and certainly not continuous at x equals 0, because the graph of this function, as you know, is something like this. And if this were minus 1 and this were 1, the definite integral we'd eventually be wanting to look at is this area under here. So this function goes off to infinity, it is not defined at 0. Also, we have a second problem. The antiderivative of 1 over x squared is minus 1 over x. You can easily check that. That function, as I say, satisfies big F prime equals f. It's an antiderivative, but big F is not defined itself at x equals 0. So we actually have two of the hypotheses violated here. The function's not continuous as it's supposed to be on the interval in question, and the antiderivative does not exist somewhere in there. Watch what happens. Thus, if you try to evaluate the indefinite integral, or the definite integral from minus 1 to 1 of 1 over x squared dx, you could very easily say, well, that's minus 1 over x, the antiderivative, which is correct, from minus 1 to 1, except that this very first equal sign is wrong, because this equals only works if the fundamental theorem of calculus holds, and that only holds if the hypotheses hold, and you have violated two of the hypotheses. Watch what happens if you blindly go forward now. I don't like to have minus signs, so let me pull that out front. So it's minus 1 over x from minus 1 to 1. And so it's minus, put the 1 in, 1, minus, put the minus 1 in, minus 1. That becomes 2, so this is minus 2. However, if this area, which is definitely positive and probably positive infinity, is equal to minus 2, we have major problems. The reason is you did a calculation without thinking. You have to watch it in calculus. You can calculate as much as you like, but if you don't give thought to see whether the calculation makes sense, you could end up with this sort of nonsense. Be sure and keep that in mind. Here is where we finally talk about how definite and indefinite integrals are related. We've hinted at this, But now let's make it specific. Notice, the first thing to notice here is, previously we've said any antiderivative can do in the Fundamental Theorem of Calculus Part 1. Let me show you why that's the case. If big F is any antiderivative of a little function f, then look at the following. If you take the definite integral of little f of x dx from a to b, that by the Fundamental Theorem of Calculus Part 1 is supposed to be any antiderivative in here evaluated from a to b. Now in general, if f is any antiderivative and I want to write an arbitrary member of that family, that infinite family, I would write f of x plus c, wouldn't I? Now, I'm going to show you that you never have to put the c here. Watch what happens. This is this evaluated at b, so this is f of b plus c minus f of a plus c. And notice what happens. The c and the minus c, whatever c was, is canceled out, adds up to 0. So this is f of b minus f of a. So we can always omit writing c. So when you're doing a definite integral and you want to put an antiderivative in here, do not feel obliged to put plus c. It's going to cancel out or add to 0 in the end anyway, so just don't write it, and it'll make things simpler. Thus, we can actually write the following connection between the definite integral and the indefinite integral. The definite integral rather, is equal to the indefinite integral evaluated from a to b. All I'm using here is the proper notation for f of x plus c that we developed before. Now, isn't that nice? This notation has the a and b here in the front, indicating that it's a number. This notation does not have an a and b, indicating that it is a function, and a and b are out here to indicate the connection between the two. This is why the notation was invented the way it was. There are some other notes that I wanted to gather here to pass on. Here's one, and it's really just an example to show you how this works. If you want to know the definite integral from 0 to pi over 3 of secant squared x dx, then all you need to find is the indefinite integral of secant squared x dx and evaluate it from 0 to pi over 3. Now, of course, this is one we've done before. What function has derivative equal to secant squared? That would be tangent x. So this becomes tangent x evaluated from 0 to pi over 3. And evaluating upper minus lower, it's tangent of pi over 3 minus the tangent of 0. Now you may remember that the tangent of 0 is 0, but you may not remember what the tangent of pi over 3 is. So again, if you want, go to your small drawings of right triangles. You may remember the one for pi over 6, in which the sine, which is the opposite over hypotenuse, is 1/2, which forces this side to be square root of 3. And then the other angle, of course, is pi over 3. And the tangent is the opposite over the adjacent, which means the tangent is just square root of 3. And that ends that example. But the first part is really what I wanted to pass on here, that if you rewrite this with the indefinite integral symbol, you may recall things that you've already seen before. And that's the point of it. Secondly, although we already know that if you take a definite integral and calculate it, what you get is net area. Because there may be some above the x-axis, below the x-axis, and it'll add up to whatever it adds up to, which may be positive 0 or negative. So it's not always area. Although that's true, we can find total area. We see that if we take the indefinite integral of the absolute value of the function, that will force all parts of the function above the x-axis. This will give us the total area. So there's no net involved here. And here's the idea in pictures. If you have a function that has a part above and below, like this one does, and if you then replace it by its absolute value, so if this is f, and I now want to know what the graph of absolute value of f is, what am I going to have? I'll have this part to here because it's already positive, no change. This other part will then flip up. And now in computing this as a definite integral, I am getting actual area, which reflects the total area that you would have to paint if you were thinking of this geometrically. Whereas this, when you add these two together with the definite integral, you would get only net area. So total area can be calculated by taking the absolute value of the function in question. One last note, and this is a reminder and a piece of terminology. The indefinite integral f of x dx is a function. It is a function in the variable x. That's what we saw previously. Whereas the definite integral from a to b of f of x dx is a number. And notice there is no x involved. The variable has disappeared because it's been substituted for by numbers, a and b. So what can we say as a result of that? So the variable of integration in a definite integral doesn't matter. It doesn't matter what letter you use. So the variable of integration, although I've written x here, really makes no difference. In fact, this variable is often called a dummy variable, like a closed dummy, standing in for a person. A dummy variable, also called a placeholder. So that means that that original integral, a to b of f of x dx, could also be written, if I so choose, as the integral from a to b of f of t dt. I can change it to another letter, f of y dy, and so on. As far as the definite integration goes, the letter inside that you use for a variable is a placeholder. It doesn't matter what you use. Now, if you're connecting this up to a picture, then of course the x value and the t and the y will represent something geometrically in the graph. But as far as the integration goes, it does not matter what the letter is. Now we'll take a moment to develop a theorem which is really very nice and is used in the development of the fundamental theorem of calculus part 2 and in a notion of average value of a function, which we'll talk about later. This is called the mean value theorem for integrals. Now this is as opposed to the mean value theorem for derivatives, which we saw earlier. Here is the idea. It's very geometrically motivated. Suppose you have a function, something like this, say. And here is our function f of x, and we'll assume that it is a continuous function. Now it is going between, say, a and another value b. Now notice, in this function, there seems to be a lowest place. And of course, if it's a continuous function on a closed interval, it has to have a minimum. You may remember that from the extreme value theorem. So there's a minimum value here. Say that's little m. And there's also apparently a maximum value up here, which looks like it's right about there. And we'll call that big M. So little m is this distance, and big M is this distance. And now, if we wanted the area under this curve, and I drew it above the x-axis, so we're just talking about area right now, notice that this area is certainly bigger than the area of this little rectangle down here with height m and base b minus a. And it's certainly less than the area of this large rectangle with height big M and base b minus a. It's caught between there somehow. So if you want to draw a graphical picture, you might have something like this. Here is the actual area that you would like to find. And the base, of course, is b minus a. Now that's certainly bigger than the area of the small rectangle with height m and base b minus a. And it's certainly less than the area of the large rectangle with base b minus a and height big M. So this is too large, and this one is too small. Now, the natural question is, if you let rectangles grow from this small rectangle to this large, that is, if you imagine you had a bar here and you just let it go upwards, at some point it crosses from being too small to being too large, and there ought to be a place in here, it seems reasonable, that there ought to be a place where the bar would be exactly the right height to give you the area under this curve. And that is the question that is asked here. Is this equal to the area of some medium-sized rectangle here with base b minus a and some unknown height? Is that going to always be true? And if it is, how do we find it out? Well, the fact is, if f is a continuous function on a closed interval, it is always true. And that is exactly what this mean value theorem says. So this is the mean value theorem for integrals. And it starts off with the simple hypotheses I mentioned, that f is continuous on a closed interval. Then, here's what the mean value theorem says. It says there is at least one point, which we'll call x star, in the interval AB, such that the actual definite integral, which is more general than area, although I did draw it as a picture of area on the previous page, is actually equal to what? The area of a particular rectangle. Well, that rectangle will have base b minus a, of course. What will the height be? Well, it will be determined by some value of the function. What value? The value of the function at x star. So there will be some points so that if you take the functional value, that will give you the mean, or if you like the word average, height of the function. And that's what the theorem says. Now this one is interesting enough that I'm going to go ahead and prove it and pull together some of the notions you've seen before. So let's go ahead and see how this might be proved. Remember, we have a continuous function on a closed interval. So by the extreme value theorem, which I mentioned before, f assumes both a maximum value, which we'll just call big M, and a minimum value, which we'll call little m, on that closed interval AB. That's what I said in the original picture. So what does that mean? That means that if I take any value x in the interval AB, then the f of x is caught between big M and little m. The height of the function, as you saw, is always between the smallest value and the largest value of the function. So, with that in mind, if we have inequalities like this for the function and two numbers, that will also hold true for definite integrals corresponding to that. So the definite integral of little m dx is then going to be less than or equal to the definite integral of f of x dx, which is what we're actually looking for, remember. And that's less than or equal to the definite integral from a to b of big F of big M dx. So the middle one we don't know, but the ones on the end we do know. This is a height of m, so this is going to be a rectangle of height m and base b minus a. So this is really just m times b minus a. You can easily check that. And then the integral in the middle remains unchanged. And over here we'll have big M times b minus a. So that's the rectangle with height big M and base b minus a. And then if I divide through by this common b minus a, notice what I have now. I have little m less than or equal to the definite integral from a to b of f of x dx times 1 over b minus a less than or equal to big M times b minus a. This number in here is, well, it's a number. The definite integral is a number, and 1 over b minus a doesn't change that. But this is a number, and I guess I shouldn't have written that there, since I've already divided that out. This is a number between little m and big M. This is a number. Now, what's good about that? Well, let's see here. If I draw a quick sketch to see what I've got big M here, and maybe somewhere, maybe little m's down here, who knows. And then I have a function that has some sort of a value like that. And there's the function f. And here's a, say, and here's b. Then what I've discovered is, this is a continuous function, remember, between little m and big M. And I have this number, which is somewhere in there, maybe here. Well, if this is a continuous function and you go over to the curve, there has to be a point here. That is given to us by another theorem we saw earlier called the intermediate value theorem. So let me write that down. By the intermediate value theorem, for some value x star, and see that would be the value x star down here, in the interval AB, f of x star, which is just this height here, will have to be the same thing as this value of this number in here. So it has to be equal to 1 over b minus a, the integral from a to b of little f of x dx. And if you take the b minus a over to this side, you have exactly the statement of the mean value theorem for integrals. And that's where we end. So we got to use the extreme value theorem on the other page. We have the intermediate value theorem here. And this is a nice example of how the calculus builds on previous results. So let me show you again what this looks like geometrically. Thus, if you have this situation where you have some sort of a function, as long as the function is continuous now, here's a, here's b, then the theorem says that somewhere in here there's an x star, so that if you take this height of f of x star and you use that as the height of a rectangle of base b minus a, because this distance is b minus a, remember, then the area under that rectangle, or in that rectangle, will be exactly equal to the area under the curve. That's what the theorem says exists. And that's nice to know. And we will use this later, as I said, in the Fundamental Theorem of Calculus Part 2 and later applications. So keep this nice result in mind. Now it's time to look at the second half of the Fundamental Theorem of Calculus. Fundamental Theorem of Calculus Part 2, and we'll see how the two fit together a little bit later. Here, instead of giving you a proof or a development, I'll try and just give you the idea. Here is what we are talking about. Imagine that we have a function, f, and it is defined as usual between points a and b, so it's on some closed interval. Now, what I want to do is talk about how the area changes as we move from left to right. So what I'm going to do is pick an arbitrary point here, and I'm going to call this x. Now, if I call that x, I'm going to have to be careful about my other variables. So I will call the horizontal axis the t-axis, and think of this as a function f of t now. It won't change anything, but it will allow me to have this x, which will now vary from a to b. As we move from left to right, the x will include more and more area. So what is the actual representation of this? Well, it is the integral from a to x of f of t dt. And we did talk about how the variable was a dummy variable, so any letter in here will do. But since I'm using the x up here, I don't want to confuse things by also using an x for a second purpose down here. Now, by the Fundamental Theorem of Calculus Part 1, we know that this is equal to big F of x minus big F of a, the upper minus the lower, provided that f prime is equal to little f. That is to say that big F is an antiderivative of little f. This suggests, with the x up here, that if I treat both sides as a function of x and I just differentiate, what I get on the left is the derivative of this integral, which is unusual so far. And on the right, look what happens. The derivative of f of x is f prime of x. The derivative of f of a, that's a constant, so that's 0. And big F prime of x is equal to little f of x. So look what apparently has happened. That I have taken this integral of little f of t and taken its derivative and ended up with the function inside. It appears that I found a way to undo the integration by differentiation. And that is the key notion behind the Fundamental Theorem of Calculus Part 2. Here is a statement of it. It really comes in two parts itself. If f is continuous on some interval I, then automatically f has an antiderivative. On the same interval. So every continuous function is guaranteed to have an antiderivative, or, if you like, an indefinite integral. Then, if we pick an arbitrary point, any point whatsoever, say a, in I, and a is completely arbitrary. It is in the interval I, though, so the function is certainly defined at it. then here's what we can say. This first part says that little f has an antiderivative. Now I'm going to actually show you one. Then the following function, which I'll label with the big F, which is the integral from a to x of f of t dt, which is a function of x as x moves from left to right. Remember, this measures the area. This function here is one such antiderivative. So not only am I told in the first part that little f has an antiderivative, but here's an example of one of them, this integral. Meaning, if it's really an antiderivative, then if I take its derivative, which is the same form I had on the previous page, the derivative of the integral from a to x of f of t dt, I should get back the original function f, and I do. That's the power of this second part of the fundamental theorem of calculus, that if you differentiate an integral that goes from a to x, where the a is totally arbitrary within the interval that the function is defined, then the differentiation and the integration undo one another. It's as though they cancel each other out, and you end up with just the function that was underneath here. Let me show you what I mean by an example, or a couple of examples. This one will be a simple one. Someone may ask you, what is the derivative of the integral from minus pi to x of cosine t dt? Well, all you need to do is see that this is in the correct form. There's an x at the top. There's an arbitrary constant down here where the function is defined. And this function is defined everywhere. So that means the derivative is just cosine x. I just take the function under here, replace the t by x. That's all there is to it. Again, this function involves a constant, in this case minus pi, but it could be any constant where the function inside is defined. Now let me show you one other example where the chain rule is needed, which is just to keep in mind that there's some aspects of this that are sometimes a little more clever than you need to think about generally. This function under here, this whole integral, remember, is an antiderivative, so I could think of it as a big F of x. In this example, if I want the derivative of the integral from 1 to x squared, now notice it's not x up here anymore, of cosine t dt, I have to be careful. So how do I be careful? Well, if you think of this as not big F of x, but big F of x squared, you'll be on the right track. Because then you can think of x squared as u, and then this becomes a function of u. In other words, we're doing what we always do in the chain rule. If we have a function of another function, we'll take the derivative of the outside function, which in this case is big F, and then afterwards multiply by the derivative of the inside function, which is x squared. So the result should be, if this were just an x, it should be cosine of x. But the x is really x squared, so that's what I'll put here. And then I will need the derivative of the inside function, which is just 2x. In other words, if I put it in terms of the big F here, this is big df du times du dx, because remember, u is x squared here. And so this explains what's going on. So be careful when you apply the fundamental theorem of calculus part 2. If the upper limit is not a simple x, the chain rule is necessary. The lower limit also has to be an arbitrary constant where the function is defined. As long as that's going to be the case, you'll be fine. But in general, just be a little careful. I've already suggested that integration and differentiation are inverse processes, and let me go ahead and just show you that right now, specifically. And this fact comes out of the two parts of the fundamental theorem of calculus. The fundamental theorem of calculus, part 1, if we apply it this way, suppose I write a to x instead of a b up here, and instead of writing f of x inside, I'll write f prime of t dt. Now the fundamental theorem of calculus says, part 1, that I should find an antiderivative of the function inside here, but the function itself is a derivative. The antiderivative of f prime is just f. And then I evaluate that antiderivative at the upper minus the lower. So I have f of x minus f of a. So one may describe this by saying the integral, which is this outer operation, of a derivative, the inner function, recovers the original function. Now you might say, well, it doesn't quite. It recovers f of x, and then there's this minus f of a. But if you have f of x here, you can easily find out what the f of a is. So it really does recover it. The fundamental theorem of calculus part 2 then says, if you take the derivative of the same sort of integral from a to x of f of t dt, then you get back f of x. And this is pretty much the way the fundamental theorem of calculus part 2 looked. This says if you take the derivative, that's the outer operation, of the integral, which is the inner function this time, you recover the original function. So the two parts of the fundamental theorem show you that differentiation and integration are inverse processes. Not quite inverse in the case of integral of a derivative, but the constant is really not a difficulty. Basically, they undo each other. And you want to keep that in mind. Now for some exercises. The first one here will be to evaluate this integral. The integral from 1 to 4, definite integral, of 1 over the square root of t minus 3 times the square root of t dt. Try that. This is straightforward. Let us first rewrite this so that I don't have these fractions and these square root symbols. I'll rewrite this as t to the minus 1/2 power minus 3 times t to the 1/2 power dt. That's usually a good idea. And then we'll apply the rules we know, which is that to do the definite integral, I need to find an indefinite integral of this. I need to find an antiderivative of this part. Well, I know how to do that for powers. I add 1 to the power and divide by the new power. So I will end up here with t to the 1/2 divided by 1/2 minus 3 times t to the 3/2 divided by 3/2, all evaluated from 1 to 4. And then I put the 4 in and evaluate this, subtract this evaluated at the 1. It's f of the upper minus f of the lower. In that case, moving this 1/2 up, I will have 2 times square root of 4 will be 2, minus 3 times, bringing this up, it's 2/3. And then I'll just write 4 to the 3/2 here so we can talk about that. Minus, and now I put a 1 in. I'll have 2 times 1 minus 3 times 2/3 times 1. Now first I note in the second part that 3 times 2/3 is 2, so 2 minus 2 is 0, and that's gone. In the first part, I have a 4 here. The 3 knocks this out, gives me a 2. When you're faced with 4 to the 3/2, my advice is always do the square root first. Then the square root of 4 is 2, and then 2 cubed is 8. Then 8 times 2 is 16. We end up with 4 minus 16, and the answer is minus 12. So this definite integral turns out to be the number minus 12. If you were to graph this, you'd find out that the net area looks like minus 12. Let's look at one that's got a little bit more to it. Suppose you have the function big F of x is the integral from 4 to x of the square root of t squared plus 9 dt. Let's do 3 things. Let's find f evaluated at 4, f prime evaluated at 4, the first derivative, and f double prime, the second derivative, evaluated at 4. Go ahead and try that. Let's see how this worked out. There's our function, which is a definite integral from 4 to x of square root of t squared plus 9 dt. If I want to evaluate it at 4, I put the 4 in for x everywhere. So I'll have the integral from 4 to 4 of square root of t squared plus 9 dt. Well, now, this is an integral that goes from the same number to the same number. The function doesn't matter. This is like finding the area above a single point, and so the area, of course, is 0. For the first derivative, f prime of x, before I do f prime of 4, let's do the derivative in general. That is the derivative with respect to x of the integral from 4 to x, square root of t squared plus 9 dt. Well, that's exactly the situation that the fundamental theorem of calculus set up for us. Arbitrary constant down here where the function's defined, and then an x upstairs. So this just becomes the square root of x squared plus 9. So that means f prime at 4 is then the square root of 16 plus 9. That's 25, so the answer is 5. And finally, just for fun, the last one, the second derivative, we'll have to get before we can do its evaluation at 4. There's the function, so that's x squared plus 9 to the 1/2 power, so that's 1/2 x squared plus 9 to the minus 1/2 power times 2x, derivative of the inside. So that's x over the square root of x squared plus 9. That's easy enough. And so f double prime at 4 becomes, let's see, 4 over, well, we put 4 in here before. 16 plus 9, that was the value we got there, so it's 4/5. And that is, I hope, what you got here, and is only the beginning of what we'll be doing with integrals later.